Hey folks, Ms. Gosling here. In this video, you're going to learn about the law of conservation of energy. By the end of the video, you'll be able to solve problems involving the law of conservation of energy. So let's go ahead and get started, shall we? So the law of conservation of energy is very straightforward, and that is that energy cannot be created or destroyed, only changed. So what that means is if I hold an apple above my sister's head, and it has let's say it's got 10 joules of potential energy as it's sitting above my sister's head. And then I drop it. When it hits her head, it will still have 10 joules of energy, but that energy will now be kinetic instead of potential. So with the law of conservation of energy, what we're saying is that if there's no way for the energy to leave my system or enter my system, the total energy in my system will be constant. So another good example of the law of conservation of energy is a roller coaster. So in a roller coaster, I have some potential energy at the top of my highest hill, and throughout that roller coaster, some of that potential energy will be kinetic, and some you'll have different balances of kinetic and potential energy. So for example, if I start at the top of this hill here, let's go ahead and do this in a slightly nicer color than that. So I'm going to start again at the top of this hill here with some kinetic energy, or with some potential energy, because I am not moving, we'll say, but I am at the top of a hill. So I have potential energy. As I go down that hill, my potential energy will turn into kinetic energy. And then I'll go up that next hill. And when I get to the top of the next hill, I know that I'll have some potential energy since I'm higher than I was at my deepest point, but I'm not as high as I was at my highest point. So that means that not all of my energy will be potential. Some of it will still be kinetic. So that's really kind of the key of our conservation problems. It's going from point to point and figuring out what kinds of energy you have at each point. So let's look at an example. A cart of mass 100 kilograms holds 10 people, each with an average mass of 50 kilograms. If the cart is at rest at the top of a 15-meter roller coaster hill, how fast will the car be traveling when it hits the end of the hill? So let's go ahead and start by drawing a picture. Here is my roller coaster hill, and here is my cart with its 10 people. So that's going to have a mass of 100 plus 10 times 50, since that's the total mass of the cart and everything in it. And my cart is initially at a height of 15 meters. But then it's going to roll down the hill until it reaches the bottom. At the bottom of the hill, the mass will be the same, so it'll still be 100 plus 10 times 50 kilograms, but its height will be 0. So what we want to do is figure out how fast the car will be traveling when it hits the end of the hill. So here's what we know. So we know that the initial height, which I'm going to call height initial, is, and actually, guys, I'm going to solve this a little differently from how you're used to. I know we like to do our givens, unknowns, equation, substitution, solution. What I'm going to do is I'm actually going to do this using what I call the before and after method. So I'm going to start with my before and then look at my after. And what I want to do is calculate my total energy before and my total energy after. Because remember, my total energy before is equal to my total energy after. So at the very top of my hill, my cart has potential energy. So we know we have some UG initially, but we don't have any kinetic energy since we're not moving. So I'm going to go ahead and note that here. No K. Afterwards, we have kinetic energy, but we have no potential energy because we're no longer off the ground, we're on the ground. So from there, I can expand out my energy equations. So we know that my gravitational energy is equal to m, my initial mass, times g, times my initial height. And really, we're going to assume for these problems, guys, unless otherwise, that our mass is constant, so I don't need to worry about initials and finals. It's going to equal mass times gravity times my initial height, and that is going to equal the kinetic energy at the end, or 1/2 times m times my final speed squared. From there, I can start putting in my numbers. And what I like to do with these problems, guys, I like to create a diagram like this that's color-coded with my before and after. And I like to use that as my place to list my givens. So you can see I have H, I have M, and G is always a given. And I have M listed here at the end. So my mass is 100 plus 10 times 50, or 600 kilograms. I had to think about that for a second. So my mass is 600 kilograms, G is 9.8, and my initial height is 15 meters. And that is going to equal 1/2 times my mass again, which is not going to change, times my final speed squared. And from here, it's just algebra. And you'll notice I left V final as a variable because that is what I'm trying to find. So let's go ahead and start by canceling out our 600s. I have a 600 on both sides, which means that they cancel out. Then I can multiply 9.8 times 15. And when I do that, I find that 9.8 times 15 is equal to 147. So what that gives me is that 147 is equal to 1/2 times my final speed squared. Next, I want to multiply both sides of my equation by 2. It's going to cancel out my 1/2. And that's going to give me V final squared is equal to 294. Then it's a simple matter of taking the square root. So I'm going to again take the square root of both sides, which will get rid of my squared. And what I get is that V final is equal to the square root of 294, or approximately 17 meters per second. And there you have it, folks. I have finished solving through this problem. So that brings me to a discussion on how you approach solving a conservation of energy problem. So we want to start by drawing a picture, and really 2 pictures, one for the beginning and one for the end. So the before and the after picture. Then we want to list our givens under the picture or as labels on the picture. We want to determine what kinds of energy each side of our equation, picture has, so our before and our after. And then we can use that to expand out our E final is equal to E initial equation and solve for whatever is unknown in our problem. So let's look at a slightly more complicated problem. This time, my before is the same as my last time. So we're starting at the top of the hill. And let me go ahead and color code this properly with our before. My cart has the same mass it did before. So it's a 100 kilogram cart with 10 people with an average mass of 50 kilograms. So my mass is going to still be 600 kilograms. And the height is going to, again, be the same as well. So now we are 15 meters off the ground. But our new end point is figuring out how fast we're traveling halfway down the hill. So instead of looking at the end, we're going to look at a new end point, and that is halfway down the hill, where our height is going to be 15 over 2, or 7.5 meters. Now, we have the same mass that we did before, so we're going to start with that same 600 kilogram mass. And what we want to do is figure out our speed. So let's go ahead and expand that equation out. So our total energy before is all potential. So we have just potential energy to start off. And that is going to be equal to my total energy after. Now, my afterwards, I'm both off the ground at that halfway point. I'm both off the ground and I still am, and I'm starting to move at this point. So that means I have both potential energy and kinetic energy to worry about. So from here, I can go ahead and expand out my equation. So I get that mg times my initial height is equal to mg times my final height, which I'm having some trouble writing here. Let me go ahead and clean that up a little bit. So m times g times hf plus 1/2 times my mass times my speed squared. Now you'll notice I have a mass in each one of my terms. So if I divide this whole thing by mass, it will cancel out in all 3 of my terms, giving me g times my initial height is equal to g times my final height plus 1/2 times my speed squared. So what I'd like you to do is take a moment, pause the video, and see if you can finish solving the problem. Okay, so hopefully you guys took the time to pause and solve that out and got that your final speed was 12.2 meters per second. On the right here of the screen, you can see all the steps and the algebra for solving that problem. So if you didn't get 12.2, try to figure out where you may have gone wrong and add that to your notes. So with that, let's go ahead and talk takeaways. First of all, energy is conserved. That's very important. And second, we can use conservation of energy to solve problems. So we can take the fact that energy is conserved and use that to figure out what's going to happen to different objects as they move and as the types of energy that make them up change over time. So with that, it is your turn to try solving some conservation of energy problems. Best of luck and happy solving.